Hello, in this video we are going to summarize the concepts of Swin transformer that we covered in the previous videos, and we are going to add some details like time complexity. Okay, let's start. We are going to go over the Swin transformer architecture, and we are going to talk about these two papers. Mainly we are going to talk about the Swin transformer, the first paper, and also we will talk about some details from the second version. First we talked about the VIT. And in VIT, each image is divided into patches, and each patch is now a token. And the idea is that we are removing the sparsity of the connection constraint that we have in CNNs. So now, one patch, for example, from the top left corner could have relationship with a patch from down right corner. Okay? And that is known to be the reason that VIT is better than CNNs. Okay? And VIT has two main challenges. The first one is input size dependency, which means that if I have a larger input size, I need to have more tokens. For example, let's say my patch size is 1 by 1 pixel. In that case, for an image with this size, 256 by 256, I need 63,000 tokens. And for a full HD image, I need over 2 million tokens, which is computationally very expensive. The other idea is that, let's say we don't go for 1 pixel as the patch size, and we say, okay, let's have 16 by 16 pixels. In that case, we are losing some details. For example, let's consider this patch. Maybe in this patch, I have two different objects, but if I consider the whole patch as one token, I'm losing that information that is inside that patch. And these are the challenges with VIT. So in Swin transformer, they are trying to find a middle ground and solve these issues. And the architecture they provided has 4 stages, and they have different variants, but we are going to only talk about the Swin T, where the layer numbers are 2262, and C number of channels in the first stage is 96. So for the first stage, I have 2 layers, second 2 layers, third stage 6 layers, fourth stage 2 layers, and this C here is 96. And in our code, we saw that in Swin transformer class, we have these 4 stages. And if you look at the size in 4 stages, we can see the size of the images are shrinking and the number of channels are increasing. So we have a hierarchical structure. Our structure, it looks like this. We get the input image, then we get to the first stage, second stage, third stage, and fourth stage. And every time we go down, the size of the image is decreasing and the number of channels are increasing. And in the code, we saw that for this patch partition, we are using patch merging. And patch merging basically is going to create this hierarchical structure for us. In our code, we show that using patch merging conf, when we are using a conf2d, we are able to perform this patch merging, and the idea was to have the kernel size and stride equal to the downscaling factor. In the GitHub code, they use a different class called patch merging, where they are using unfold and also a linear layer. And for the unfold, again, the kernel size and stride, they are both equals the downscaling factor. And for the linear layer, they are just correcting the size of the output. For example, let's consider the first stage where the input is 224 by 3. So first you find what is the new size of the window should be. You can find that from here by dividing the height by downscaling factor. For the first one, it was 4. So 224 divided by 4 is going to be 56. So you have the 56 as the new height that you have, and or also the width, and then you put that in the patch merge, which is in an unfold, and it's gonna provide you this one. After you reshape that, you will get this. So you're getting 48 as the number of channels, and then you have 56. Okay, I'm just gonna send with permute the channels to the end. So now you have 56 by 48. Now I need a linear layer just to correct the number of channels. Okay, so in the GitHub code they use this one, but in our code we use this one, which is simpler. But there might be a reason, maybe in terms of computational cost, that they decided to go with that one. I'm not sure, but please let me know in the comment what do you think, if you prefer to use this class or you prefer to use this class. Okay, and then we started talking about the Swin transformer block, and you can see the details here. And in our code, in our stage module class, we see the Swin transformer blocks. The first one was the normal one, and the second one is the shifted one. One important point was that for Swin transformer blocks, the input and outputs, the size are equal. For example, for stage 2, after patch merging, I get to this size, and this size is gonna be also the output of the Swin transformer block. Now we have this hierarchical structure that we created. Let's focus on the last stage. In the last stage, where we have the high-level feature map, we see we have 49 pixels, and for us, each pixel now is a token. Then we said for the other stages, we are going to divide them to 7 by 7 windows and then consider each one independently. So for each one, I have 49 tokens that are related to each other, but there is no relationship between these windows. As the result, for the first stage, I have 64 windows, second stage 16, third stage 4, last stage 1 window. Now let's talk about time complexity. If I have two matrices and the size of the first matrix is I by j, it means that I have I number of rows and j number of columns, and the second one I have j number of rows and k columns. The time complexity of that is gonna be I times j times k. Okay? And considering our code, first we had a linear layer just to get our q, k, and v. So we are going to have one weight here, and the size of that is gonna be 3c by c, and the size of input is c times hw, and the output is gonna be 3c times hw. Okay? As the result, if we use this formula, we are gonna get this. So we are gonna get 3c, which is our I, times c, our j, times hw, which is our k. So this is gonna be the time complexity for this linear layer. Now let's talk about the time complexity of our attention. Again, we are going to use this formula. So I have q times k transpose inside the softmax, and then we are going to multiply to v. So first, our q, the size of q is hw times c, k transpose is transpose of that, c times hw, and size of v is also hw times c. So first we multiply q times k transpose, the size of that is going to be hw times hw. What is the time complexity of this? That's going to be this one. So it's gonna, this is our I, j, and k. So it's going to be hw to the power of 2 times c. Now let's multiply this green box to this orange box, which is basically the result of the softmax to the v. So the result of that is going to be hw times c, which is basically our output. So time complexity of that, now I is hw, j hw, and k is c, and this is going to be our time complexity for the multiplication of the output of the softmax to the value. Also, we had another linear layer, so let's calculate for that one. This time the size of the w is c by c, which we multiply to x, c times hw, and z is going to be c times hw. So time complexity of that is going to be I times j times k is going to be hw c to the power of 2. Okay, now let's put everything together. First we have this linear layer, and we just calculated its time complexity. Then for our dot product similarity, first we calculated the multiplication between q and k transpose, and that is the time complexity of that. Then we had the output of the softmax multiplied to value, which here we can see the attention multiplied to value, and this is the time complexity of that one. And at the end we had this linear layer where we just calculated its time complexity. So if we add all of them together, we get this one. So this is the time complexity of MSA, one MSA, for doing all of these things. And the important point here is that this time complexity with respect to HW is quadratic. Okay, this is the time complexity of MSA. And in our calculation, let's say our window size is M. So what happens? So for one window, H is M, W is M. So for example here, instead of HW, I'm going to put M to the power of 2. Here HW to the power of 2 is going to be M to the power of 4. So this is the time complexity of one single window. How many windows we have? Simple. We just divide the H by the size of the window times the divided W by the size of the window. Okay. Now, what is the time complexity of all of the windows? We just multiply the number of windows here to the time complexity of one window. Now we can see we can cancel these two M's here with this one and these two with the power of 2 here. So at the end, I'm gonna get this time complexity for our window MSA. So it's gonna be 4HW C to the power of 2 plus 2 M to the power of 2 HWC. And now you can see with respect to HW, it's linear. So from the power of 2, we got to the power of 1, which makes sense. We calculate only inside each individual window, and then we see how many windows we have. Okay. So this is the time complexity that is covered in the paper. Let's go forward. Now let's talk about the independency of the tokens. Let's consider two independent windows. What that means? It means that the tokens inside the yellow window, they are related to each other, but there is no relationship between these tokens. For example, even if these two tokens are very close to each other, and maybe they are part of an object and we want to have a relationship, now in this new design, they are not related to each other. To address this challenge, they provided an idea called shifted window, where they are shifting all of the windows at the same time to the right and down to the half of the window size. For example, here, if window size is 7, I'm gonna shift everything 3 pixels to the right, 3 pixels down. Okay? And if we do that, in the new shifted window, these two tokens now, they fall inside this new window and they have relationship with each other. Okay? And they showed that by doing this shifted window, they're actually getting better results than if they don't do that. So for their classification comparison, for object detection comparison, and also semantic segmentation, they show that for all of them, they are getting better results if they use this shifted window idea. Let's go back to our Swin transformer block. And in our Swin transformer block, we can see, for example, here, first we have this window MSA, then we have this shifted window MSA. So we have both of them inside our Swin transformer block. Okay, now we are going to go forward and talk about the details inside this Swin transformer block. So in the code, we showed that we have this class called Swin block, and we show that we need to create residual, prenorm, window attention, and feed forward. For residual, we showed the class that we are going to use. Also for our layer norm, we showed that in the Swin transformer version 1, these are before each block, and in the paper group norm where they compare different normalization methods, they have an image here that shows the layer norm, but we explained that this layer norm is actually different than what we do. We actually normalize each individual that here is shown in this red rectangular, each individual token with respect to itself. So we are not normalizing all the blues with respect to each other. We just consider this one with respect to each other, or for example, this one, okay, independently. And the reason is that each one of them is one token. Okay. And in the code, we showed that for doing that, inside this layer norm is going to be the dimensions that we have. And also in the version 2, they showed that if they put the layer norms after the blocks is better. Why? Let's say in version 1, my input comes in, it gets normalized, it gets an attention, and attention is provided a large value. So the large value comes here, it skips from here, and then propagates over the layers. So we don't want that to happen. So that's the reason they put the layer norms this time after the blocks. So here, for example, I get the inputs, it's gonna get the attention, large value from that, but it hits a layer norm. So it's gonna be normalized. Even if it's a skip from here, it's still normalized here. So that's the reason they decided to put the layer norm after. And in the second version, they showed that where we have so many blocks, we would end up having the more variations if we use the pre-norm, which are these solid lines, compared to the post norm where we put the layers after the blocks. So if I do the post norms, I'm gonna have less variations. Okay. And in our code, we can simply reorder that to get to the post norm. Okay. The next thing we covered was this MLP block that is basically a 2-layer fully connected neural network with glue activation function. And the glue is this blue line compared to the ReLU, which is this orange one. The next thing that we covered was this cosine similarity, which is introduced in second version. In the first version, where we are calculating Q times K transport, we are basically using dot product similarity. And we show that in the code that first we have this scale, where this scale is basically this square root of this D. And then we show that our Q, K, and V. So we have the Q, K, V. And then we perform this dot product here and multiply that to our scale. Then we added this positional embedding, this B. We put that inside the softmax, and at the end we multiply the attention output of the softmax to the value. Okay, this is what we did in dot product similarity in version 1. But in version 2, they said that it's better to use cosine similarity instead of dot product similarity. So cosine similarity is basically dot product similarity, but it's divided by the norm of the vectors. Okay. And also they have one value called tau, which is a small value just to compensate for the small output of the cosine similarity. Because when you have the cosine similarity, you're dividing by the norms. So the value of that is going to be a small. So you want to have multiply that with bigger numbers to make it bigger. So or divide that by a small number, which is used here. So tau is 0.01 and it's the learnable parameter. And in the code, we showed that we define tau here. And then to perform the cosine similarity, here we normalize Q and K with respect to last dimension. And then we perform similar things, but this time we are going to divide that by that small number. And the rest is similar. We just add positional embedding, put it inside the softmax, and then multiply the attention to value. So cosine similarity was not originally implemented in the GitHub repo that we have, but I tried to modify the code to have the cosine similarity. So please let me know if you are seeing any issue or you have a different understanding of what should be implemented. Okay? Okay, now let's go over the padding. We said that here that we are going to have a shifted window. And when we shift the window, we are going to have empty spots here. Okay? And for the empty spots, they decided to do cycle shift, where whatever is left over from top, for example, this green section is going to come down, from left going to come, and this yellow is going to come here. Then we show that in our code, we can use the torch.roll, and if we do that, we can actually do the exact thing that we want. Okay? In the paper, they showed that if we use this cyclic shift, compared to the naive padding where we are just adding zeros, we are going to have a better speed for different stages, and for different architectures is going to be faster. But this cycle shift created a challenge for us. For example, we showed that if I have, for example, a bird in the sky here, if I do the cycle shift, that bird comes here, and as the result, half of the tokens are from the grass, half are from the sky with the bird. And this is also going to happen for the last column windows. For example, here in this new window, half of the tokens from the house, half of the token from the sky. And we said that this is going to happen for all of the windows in the last row and for the last column. And we need to have a specific type of masking to handle that. And for the last row, we showed one example of a 3x3 matrix, and we showed that how the mask should look like. And we showed that for this specific example, how this mask is going to mask tokens in the last row from what is above, and also how to mask any tokens above from the down. Also, we showed the mask for the last column, and we could see that, for example, any token here is going to be blocked from the left side, and also any token from the left side is blocked from the tokens on the right side. And in the code, we saw that whenever we have this cycle shift that we just shift with half of the size, so we are going to implement these masks. And what important point was that these masks in the code, they're not learnable, so requires grad is false. And also, we showed how to implement them in our code only to cover the last row or last column windows. So we are not going to put the mask on all of windows. We are just going to put mask on the last row windows and last column windows. Okay. Also, we covered positional embedding, and we started with absolute positional embedding, what is used in VIT. In VIT, for example, if I have a token here, I'm going to add a positional embedding to that to just tell me where that token is coming from. When you create that as a vector, you can convert that back to a square shape and show that. So if you do that, you end up having something similar to this. And for example, you can see in the center, the yellow dot is in the center. In the right top is the yellow, move to the right top. Down is here, left here. And you can see the movement of this yellow dot is going to indicate where that patch belongs in the image. Okay. And we show that for a 3x3 window size, we need 18 parameters for doing that. Also, we showed how to do the relative positional embedding, and with the less number of parameters, we are able to fully define the location of the tokens. In the paper, they showed that if they use relative positional embedding compared to the absolute positional embedding, they're actually getting better results in classification, object detection, or semantic segmentation. In general, they provided their results in terms of classification, object detection, or semantic segmentation. Okay, now let's talk about the sparsity of connection, something that we know is the reason of the success of CNNs. So by definition, we could say in each layer, each output value depends on a small number of inputs. So it means that when a kernel is on an image, so that weights from the kernel gets multiplied to the pixel values, and the output of that only relates to pixels under this kernel. So it's not related to the pixels here. Okay. And even if kernel moves to the new location, now outputs only belong to these pixels and they are not related to this. So somehow pixels that are close to each other in the image, they get more emphasized on their relationships, and pixels that are far from each other, they get less emphasized on their relationships. Okay. And that helps CNN to be successful, but that provided a constraint for us. So we could say that we have the sparsity of the connection constraint in CNNs. In VIT, they tried to get rid of that. And they said that each patch from any location of the image can have relationship with another patch. For example, I can have a patch here, and that could have a relationship with patch here. Okay? And as the result, they got rid of this constraint, and that is known to be the reason of their success. How about Swin transformer? Let's look at, for example, two different windows in the first stage. You can see I have one window here, I have one window here, but these windows are independent from each other. So tokens inside this red window, they are related to each other, but they're not related to tokens inside the screen window. So you could say for the last stage, all of the tokens are related to each other. But for the earliest stage, that is not the case. Even after you do the shift and shift all of the windows at the same time for half of the size of the window, what just happened is still these tokens are not related to these tokens. So for Swin transformer, we could say that inside each window, we don't have a sparsity of the connection constraint. So all tokens are related to each other inside a window. But overall, still we have this constraint. Still, windows are separate from each other. And pixels that are close to each other, they have more relationship with each other than pixels that are far from each other, especially for the earliest stages. The other paper that we should talk about here is Vision GNN. In Vision GNN, they try to create a graph from these patches. So they divide the image into patches and then they consider each patch as a node of a graph and they try to find the relationship between these nodes. So they are trying to get rid of the sparsity of the connections constraint. But because it's computationally expensive, they limit their number of edge. For example, they say, I'm gonna to have only 9 edge connecting each node to the others. So in that sense, we could say Vision GNNs, they don't have a sparsity of the connection constraint, but I'm gonna put an asterisk here because they are still limited in the number of edges that connects the patches to each other. In summary, Swin transformer has a hierarchical structure like convolutional neural networks, and unlike VIT, it doesn't get rid of the sparsity of the connections constraint. Also, recently Vision GNN showed a better performance than Swin transformer, and maybe graph neural networks is a promising directions for developing future vision backbones. We actually covered Vision GNN in a separate video that I recommend you to watch that video as well. And also please in the comment section let me know that what you think would be the next vision backbone. And overall I tried to cover the materials from the code and paper based on my understanding. Please let me know in the comment sections if you have a different understanding. And thank you so much again for watching this video. See you next time.